Okay, hi. Good afternoon, everyone. So today we are going to talk about HBase and give a little bit deeper dive into the new features that we have done, that the community has done in the HBase land. Sorry. Okay, so a quick introduction about us. So I am Devraj Das, Hadoop committer, HBase committer, and a co-founder of Hortonworks. And with me I have Enis, who is also a HBase and Hadoop committer, and he has been in Hortonworks from almost the beginning of Hortonworks and in the HBase team. Okay, so this is the outline of the talk. I'm going to talk about MTTR, support for rolling upgrades in the new versions of HBase, a quick update on the security front, and then Enis is going to follow up with the use cases of namespaces in HBase, some details on the compaction algorithms, compaction enhancements that has gone in recently. He's going to talk about MapReduce over snapshots, HBase snapshots, and then he's going to talk about idempotent increments in HBase. So this is a lot have gone into HBase, but this is kind of a list of things that we thought are interesting to present, so this is what we chose for our presentation today. Okay, so part one, a quick recap into the HBase architecture just to set the context for MTTR. So in HBase we have a table split into regions in a horizontal way, and these regions are hosted on region servers, so a region has only one copy in the cluster, okay? So a region gets hosted on only one server. Now, if for any reason the server goes down, right, so these are machines, that region becomes unavailable for a period of time, right? And a region server could be hosting n number of regions in the order of, let's say, 50 to 100 regions, right? So those many regions become unavailable until the regions are reassigned to some other server and that kind of a thing, right? So the idea of the MTTR work is to basically reduce this downtime. And the other thing I want to point out is this meta, right? So meta is a table that has metadata about all the other tables in the cluster. And this is also a single table. And all clients, when they start, they first look up the meta in order to find out where the actual region is in the cluster, right? So this becomes a single point of failure as well. Okay, so if this is down, new clients, at least the new clients, cannot talk to their regions, okay? Existing clients could still be talking because they would have cached the information from the meta when they connected to it the first time, okay? But new clients actually cannot talk to any of the servers in the cluster or talk to any of the regions in the cluster because meta is down. The other thing is that there is Zookeeper quorum here. So the information about where the meta server is actually stored here in the Zookeeper. And in the past, we had another table which was called the root table. Okay, so you had two interactions, one the root and then the meta. But in the newer versions of HBase, we kind of removed the root table, so there is only meta table at this point. Okay. So the key thing to note is that a region doesn't have replicas, so if it is down, your data is unavailable. Okay, so if you look at the definition of MTTR, it's the average time required to repair a failed component, right? By the definition of it. So ideally, we should have a zero downtime in HBase, right? So the data should always be available all the time, right? But the way HBase is architected, it's hard to kind of do that because, as I said, there are no replicas for regions yet. So it's hard to obtain, but it's a goal that we are shooting for. And given that HBase is used in real-time systems, it's very important to have close to zero MTTR for HBase. Okay, so yeah, a quick overview of the write path. This will further set the ground for the work, the MTTR work. So you have a client, and then there is region server, and then you have something called as write-head log here. Okay, so this is a file on the HDFS that gets appended to for every incoming edit. So let's say the client sends a mutation, so that's an edit, right? So let's say there's a put of a key and a value. So the first thing that the region server does is that he writes it to the wall, okay? So that if it went down, the data is recoverable, okay? And then you have mem stores here in the region server that is then written to, okay? So you have the data in memory at this point of time, okay, in the region server. And when the memory becomes full, you flush the memory and you create something called a store files, okay? So is everyone familiar with this architecture, or is with this kind of a, the concept of store files and walls and all that in HBase? Hopefully this gives you some idea if you're not already familiar. Okay, so store files are the persistent data sets that we have in HBase, okay? So this is the real data that is then served. And the one thing that I want to point out is that the wall files are the ones that are critical for the recovery, okay? So wall files are written to, and when they reach a certain size, they're closed, and a new wall file gets created, okay? So at the end, or during the life of a region server, you might have multiple wall files that gets accumulated. And they get deleted as and when flushes happen and compactions happen. The one thing that I want to point out is that today in HBase, there is only a single wall file, okay? So if you had this region server hosting multiple regions, all the edits for all the regions gets written to one, in a sequential order in that single wall file. And eventually it will get, that size will be reached and it will get rolled over. But then the point is that it's not the case that you have different wall files for different regions, okay? So all the edits go to a single wall file. Okay, so what happens on a failure? So the first thing that happens is that master detects a failure, okay? So there is a state in Zookeeper that is kept, and the master is watching for changes to that state. So whenever that state change happens, master gets a notification saying that particular Z node or Zookeeper node has changed state, and in this particular case, it signifies the region server has failed because that node is no longer there, okay? So master detects it, right? And then master creates tasks for wall splitting. So I just talked about the wall file, right? So he creates tasks for splitting up the different wall files that might have accumulated in the region server's directory on the HDFS, right? And after the wall splitting, the master goes and assigns the affected regions. Whoever was running on that region server gets reassigned to other servers in the cluster, okay? And the newly assigned servers actually replace all the edits from those walls into their memory, so they get a consistent view of what had happened in the earlier region server, right? And then the client is redirected to the new region server for their respective regions. Okay. So this gives a pictorial view of the flow. So this is the guy that went down. So he had written a bunch of files, wall files, and so the master creates the wall splitting tasks that actually read those wall files, and they are run in the context of the region server. Okay, so the region server reads those files, and then they create files for each region. Okay, so they split the wall and they create files that correspond to every region. Okay, so you have these files are by region numbers or region names, kind of a thing. Okay, and then once the master assigns the regions to the other region servers that are there in the cluster, those region servers reads those files and applies those edits in their memory. So that kind of gives a consistent view of the data of the state that was there in this dead region server. Okay. So after that, so what we did is that we kind of improved the situation, right? So if you notice here, there are writes going to HDFS when the region server was running, and there are reads coming out of HDFS when the regions are getting recovered. And these region servers are creating new files on the HDFS, and then they are getting read back by the newly assigned region servers, right? So there is a lot of I/O happening on the HDFS when this is happening. So we thought, okay, this can be optimized. Now, what we did is that instead of master creating the tasks for wall splitting, it instead creates tasks for something called as wall replay. Okay, so and he assigns the regions immediately. Okay, in the past, the assignment would happen, at a later point. The improvement here is that you create the wall replay tasks and also assign the regions. So the assignment is very quick for the failed regions. Okay, and then the wall is replayed, and after that, the client goes to the new region server. So there is a bunch of I/O that is saved here, which I'll pictorially show here. So the same thing, the region server was writing to the wall files, and a bunch of wall files got created, and these are read by, so these are the wall replay tasks that gets created, okay? So they are also running in the context of the region servers. They read the data from these files, and they replay directly to the newly assigned servers, okay? So the whole step of this guy writing to the HDFS and reading it, and this guy's reading it back from the HDFS is saved here. So you don't create all the I/O that was there before. So it's read and then replayed to the newly assigned servers. Okay, so this actually saved a lot of I/O, and our performance numbers show that the recovery went down to like kind of 30% or something like that by doing these changes. Okay. So as I was saying, the HBase Meta is still a single point of failure. So we wanted to address this as well. So today, in the new versions of HBase, whenever there is a change in the region assignment, the old region server stores that state. Okay, so for example, if the HBase balancer runs, the balancer balances out regions in the cluster. So the old server would still keep some state as to where the region went, what the location of the new region server is. Okay, so you kind of reduce the load on the meta. So the clients, when they fail to get the data from the old region server, earlier would go to the meta to fetch the new location. Now that interaction is no longer there. This old server still keeps a state as to where the region went in the cluster. Okay, and the wall for the meta is kept separate. Okay, so because all the region files all the region edits are intermingled, it takes a while to recover the edits if there are too many regions and all that. So in this case, we are kind of separating out the wall separating out the meta wall into a separate file. So if the meta crashes, the recovery of that is very, very quick because it has only the edits of meta, nothing else. Okay. What else? So. And then we realized that, okay, there is HDFS also in the background that basically stores all the data. And when a node is lost in the cluster, right, you also lose a data node, right? And if you have 3 replicas for the wall file, you lose one of the replicas. And in the recovery phase, when the guys are reading from those wall files, we want to actually avoid going to those failed nodes, right? Because those nodes are dead, and if the readers go to those nodes for the recovery, then they will time out, and then the recovery process gets slowed down, right? So, sorry. And also many writes will go to it because because HBase doesn't know that data node is dead yet. Like it will know in like 10 minutes or something. Like the name node will know about it, and it will stop assigning new blocks to that data node. But then until then, the HBase layer will still try to keep writing to those data nodes, and they also time out, and the whole process becomes more expensive and non-optimal, right? So we introduced something called a stale mode in HDFS. So the idea is that if a data node doesn't send you a heartbeat for n number of seconds, which is by default 30 seconds, you mark the data node as stale. Okay. So if you lose a node, that node is marked as stale, right? So for all reads, that will be the lowest priority, okay? So the reads will be sent to the other replicas, the other 2 available replicas, but not to the guy who is stale, okay? That way the block locations will be ordered by the name node, okay? So that's what this also gave a very good improvement. And it is also not used for writes, as in the name node will not schedule any block placements on those stale nodes, okay? Assuming that they are going to die or something. It's not behaving well kind of a thing. And this is just an added information that after 10 minutes, if the node is not responding, it's really dead, the HDFS will re-replicate all the data that was there on that node. So hopefully it's not really dead and that kind of a thing. But the stale mode is a key point here. So this actually saved a lot of unnecessary work that HBase was doing when nodes go down. Okay. The other thing that I want to quickly mention is that so the store files that gets created, they also have locality. So when a region server is creating the store files, when the memory becomes full, the store files gets created, right? One copy of this, one replica of the block of the store files are local to this region server, and the other replicas go to random nodes in the cluster, depending on how HDFS chooses those replicas, right? So these store files are comprised of hundreds of HDFS blocks. Okay, one copy is local, so the region server, when it is running and alive, it is reading the data local from its local disk, right? When a client sends a request for some data, a quick overview here is that the mem store is looked up, the store files are looked up, and then the region server does a merge and sends the data back to the client. Okay. Now, so there is HDFS reads happening when a region server is trying to serve data to the client, right? Now, in the normal case, I was talking about this, that there is one block of each store file local to yourself, to the region server, right? But on failures, when this region server crashes for whatever reason, the blocks for the regions are read from remote locations, because the replicas could have gone to random servers in the cluster, and the newly assigned server doesn't have all those blocks local, right? So that introduces a lot of network reads and interferes with the whole recovery process as well. Okay, so can we improve this? Seems like we could improve this by doing something called as favored nodes in HDFS. So we enhanced the create API in HDFS to take in favored nodes as an argument. So all the region files that is created here, right, by this region server are created on 3 specific nodes. One, the local, and 2 other nodes are chosen in the cluster based on how HDFS would choose the replicas, keeping in mind the failure zones and all that, right? So all the files, all the blocks of these files are stored on those 3 nodes, okay? And the HBase master is aware of this mapping, okay? So when there is a failure, when this server fails, the new server that is chosen for the regions would be the one that has all the blocks local again, right? So the new server would read everything locally. So it doesn't do any network I/O at that point. So this is more optimal than the previous case, where it would read off the network. Okay. A quick overview of the benchmark results. We did a lot of experiments in partnership with eBay on their real jobs and everything. So the baseline was, it's not readable, but it was like 180 seconds, which is 3 minutes in the old versions of HBase. And after doing all the work, we kind of brought it down to like 10x by 10x, okay, in the order of a minute or less, depending on how what the jobs are running in the cluster at that point of time. Okay, and so a quick overview of the rolling upgrades. So HBase RPC was based on custom serialization, and it was hard to upgrade a cluster without taking down clients. So if you wanted to migrate from, let's say, HBase 90 to 92, the clients would have to be brought down and then restarted, right? Kind of a thing. So that was something that we wanted to address in the newer versions. So the solution we chose was to use protocol buffers for everything, for all the messages that happens in the cluster and between the client and the cluster. And all the services are modeled as protocol buffer services. And because the requests and responses are also protocol buffers, any change in the fields and any addition or deletion of fields would be handled by the protocol buffer APIs and everything. So going forward, the expectation is that the clients don't have to be taken down, right? You could just do a rolling upgrade, and clients could just survive that kind of a upgrade, okay? And all the Zookeeper data and other system data, like the metadata table, is all protocol buffered, so that older versions of HBase can read the newer versions of this data without crashing, and vice versa. Okay. So one quick point here is that so if you have, let's say, 94 cluster or 92 cluster, and you wanted to go to the latest versions of HBase, it's a singular release. Okay. So you have to bring down everything, and there is a set of steps that needs to be performed in order to bring up the new versions of HBase in a cluster, and then clients should be started up after that. Okay, so it's a singular release in that sense. You have to bring down the cluster and bring down the clients, and then start everything back. So going forward, like 98 to 1.0 and forward, we should not be needing this kind of a downtime. Okay, a quick update on security. So HBase already had Kerberos authentication and access control at the level of tables and column families and column qualifiers, kind of a thing. In HBase 98, access control at the level of HBase cells were introduced. So this is very close to how Accumulo implements the cell level security. So you could say, when you do a put, that this cell should be only readable by so-and-so users, kind of a thing, or should not be writable by anyone else, kind of a thing. Okay, you could set all that in your API. You could use all those facilities in the new APIs that is provided for per cell access control. Okay, and there is also the concept of labels. So you could define that these cells should be only accessed by people who are in, let's say, the secret domain or top secret domain, kind of a thing, and you can have some sort of expressions based on that. So you can say, these cells, they should be visible to secret or top secret people, right? And this gets stored in the HBase store files. So these are all persistent, okay? And you can assign users to those authorization sets. You can say, add user to a secret domain or a top secret domain, whatever, right? You can create your own labels and assign users to those labels, and limit visibility via expressions like this, okay? And it's all supported in 98. And well, the feature is still experimental because there are some edge cases that needs to be addressed well, but it's getting there at this point. Okay, so at this point of time, I'll invite Enes to continue on the part 2, and then we'll take the questions at the end.
Okay, is it good? Okay, so in part 2, we will cover 4 new features as well. And we will first look at the namespaces, which is a kind of exciting feature that basically the folks from Yahoo implemented this. Basically, the problem was in Yahoo was to address the multi-tenant use cases for their big clusters. So what they ended up doing is that they wanted to abstract away a method to do per tenant grouping. So for doing that, looking at of course, like relational databases and everything, they came up with what's called a namespace. Basically, it roughly corresponds to what a schema or other namespaces in the regular databases, relational databases, as a concept. So basically, it's a way to group tables. And also, in Yahoo's use cases, they wanted to address the grouping of tables and access control domain, and basically also region server grouping and quota management per tenant. So basically the first 2 use cases is applicable at this point for like more generic, and it would be applicable to most of the HBase users, which basically you can define tables in certain namespaces, and then you can use namespaces as another dimension in the hierarchy of table, column family, and everything else. And then you can basically do access control based on the namespaces. So you can say this user should be able to create tables in this namespace, but shouldn't be able to read tables in this namespace, kind of thing. So it's another way of grouping your data. The region server groups and quotas are more like specific multi-tenant use cases. At this point, the code for managing these didn't make into HBase trunk yet. The features are out there, the patches are out there from Yahoo, and I think they've been using this for some time, but we still need to get this in and then make it available to the rest of the users. Okay, so for implementing this namespace idea, basically we had to do it in a backwards compatible way. So what we ended up doing is to implement two default namespaces, which are predefined and comes with whenever you install HBase version 96 or 98, you would have these two predefined namespaces coming up. The first one is the default namespace, which is basically the namespace for all the tables, which doesn't have any namespace. So if you have existing data in your HBase cluster and then you're upgrading it, all your tables would go into this namespace. And if you can still create tables without any kind of namespace definitions, and they would also go into this default namespace. So it would act like as if namespace isn't there. The other namespace is the HBase namespace, which is the system-level namespace that's restricted for HBase's own usage. So all the tables there basically are HBase's own table definitions for like meta table, ACL table, and the namespace table. So this namespace, HBase can basically do introduce more tables or just rethink some of the tables there, basically. So again, namespaces is a base for more multi-tenancy features coming up, and it's also a good way to do ACLs based on if you have different basically departments using HBase or different tenants. Basically, it's another way to do ACLs. Okay. So this second is the major improvements in the compaction. Basically, just to set the stage up. Basically, here's an example of a compaction. Basically, again, the writes are coming to the mem store and everything, and then when they fill up, the mem store fills up. It is written to a new data file, which is called H file, right? And then these H files are accumulated over time. And then when you have enough of these H files, you do what's called a compaction, right? You rewrite the data, and then you would come up with another H file. So the first thing that's done in this area was to make compactions pluggable. So what does it mean is that the whole storage subsystem inside HBase was basically made pluggable so that you can implement your own compaction, and you can do very different optimizations, or you can do you can basically use HBase to tune for your own needs. But of course, this also enables to change the default compaction policies, or based on your use case, have different compaction policies for your tables. So the first compaction policy is what's called an exploring compaction policy. So this is the default compaction policy from 96 and 98 and forward. So to understand this, we have to look into the previous default compaction policy, which is the ratio-based compaction policy. So this is still using the same algorithm for the ratio-based compaction policy, but it's the name implies that it's exploring. Okay, so what it is exploring is the fact that the normal compaction policy orders the data files based on their age, and then it would basically do a compaction selection, which means that it selects certain files from going over the files one by one, from oldest to the newest, and then it would select whichever is the first selection that it knows that it can compact. So this has implications on non-regular write patterns. For example, if you're doing a lot of bulk loads, or for example, if your flushes are not uniform, then this exploring compaction policy is helpful for those use cases because of the fact that instead of just choosing the first compaction that's eligible, this exploring compaction policy explores all the options within the given data files, and then it selects the best compaction that's possible. So the best compaction, in definition, is basically the compaction that reduces the most number of files. So if for example, given 10 files, there are two possible compactions that we can choose. It would choose the one which reduces the most number of files. In case of a tie, it basically runs the compaction, which is the smallest, basically, so that it can run as fast as possible. Okay. So the second compaction policy is a new one, which came in '98. This is called a stripe compaction policy. Okay. And this is inspired by the LevelDB's compaction. So I don't know whether you guys are familiar with it or not, but we cannot spend the time to talk about the LevelDB. But the inspiration comes from the fact that basically we can have more than one ranges within a region. So as you know, a region has a definite range, right? So let's say this region ranges from CCC to III, right? So and normally in other compaction schemes, what you have is that all the files would basically contain the data from CCC to III, right? So in stripe compactions, what we do is that we basically subdivide this region into what's called stripes. So every sub-region here is called a stripe, and then these stripes are automatically managed, okay? And so every stripe would also contain a range, like CCC to EEE and so on, right? So in terms of like thinking, you can think of a stripe as a mini region. So instead of this region being like a 10 gigabyte region, a stripe would be, let's say, 1 gigabyte each. So the way it works is that basically the H files forget about this L0 layer. The H files basically correspond to every H file here, the data files, correspond to the actual ranges. So this file, although the region ranges like this, this file would only contain the ranges of this, okay? Except for what's called an L0. L0 is level 0, which means that all the files in L0 contains the data from the whole range, okay? So whenever a read comes in HBase, normally you have to consult every file if this was like a normal region. But instead, since we're using stripe compaction, we just only consult the ranges, the sub-range, the files of the sub-range, basically, and the files of L0. We have to consult to this file because these files cover the whole range, but we don't have to go through these files to find our key because we know that these files cannot contain the key if we are asking a key in this area, for example, right? So basically, this is the main idea for stripe compactions. So normally the flushes go to L0, but you can also have flushes, okay, skipping the L0 completely and then directly flushing into multiple files. So in this scheme, for example, a flush would cause, if you have 3 stripes here, 3 different files. So this is a trade-off, meaning that if you basically have these ranges not uniformly divided within a given region, then you may end up with small files. But if you have very good definition for and distribution for these stripes, basically you would definitely want the flush to skip the L0 and then continue flushing into multiple stripes. Okay. So when we do a compaction in the scheme, so let's say we are doing a compaction here. Okay, we're only going to rewrite the file within this stripe. So usually, what you end up with in HBase is the region sizes. The target region sizes is between 5 gigabytes and let's say 20 gigabytes or something, right? So basically, a major compaction otherwise would have to rewrite the whole 5 gigabytes or 20 gigabytes into one single file. But given the scheme, basically you can subdivide the region range from being like 5 gigabytes to, let's say, 1 gigabyte. Then every compaction becomes at most a 1 gigabyte compaction, which improves the compaction speed, and also basically it improves the read latencies as well, because you don't even have to see these files, basically. So, but we still need the L0 because of bulk loads. So when you want to do a bulk load, basically all the files go into the L0 region. So we still need the L0, and you can also opt to have flushes go into L0 as well. Okay, and if you want to drop deletes, basically the compaction basically if the compaction sees all the files within the stripe plus all the files in the L0, then it's kind of like a major compaction. It can drop the deletes and everything. Okay? So the ranges for the stripes are kind of automatically managed with given some configuration options. And it does the stripe splits and merges as well. Okay? And this is the performance numbers. Basically, this is random gets per second versus the red is the stripe compactions, and the blue line is the default compactions. These are these are the times corresponding to compactions. As you can see, overall we would have a better read latency. And if you notice that in some cases like this, for example, the latencies would be very low because of the contention that you're doing a major compaction, and then this causes the I/O ops to basically to be saturated. Okay, so the other thing is feature is MapReduce over snapshots. So the snapshots feature has been added, I think, last year, and basically I don't want to go over it, but snapshots are basically links to immutable files, and it's a relatively cheap operation which causes flushes, and then it creates symbolic links to your data files. So the idea is to do scans on these files from the client side without going through the whole region server layer. So basically, this is very similar to short-circuit HDFS reads, where the short-circuit HDFS reads would bypass the data node and then just go directly to the disk on-disk data. So this idea is similar because we are bypassing the whole region server and HBase, and then we are directly going to the disk or HDFS, basically in this case. So we introduced a table snapshot input format, which is very similar to the table input format, which is the HBase's API for doing the MapReduce. And we've also introduced utilities in the table MapReduce util class. And basically, this feature is also not specific to MapReduce. So if you want, you can use this without using MapReduce. Basically, you can just open a scanner, which is called the table snapshot scanner from client side, and just scan from a snapshot. Okay, so this feature can be used with different deployments, HBase offline and online. So you can take a snapshot and run a MapReduce job over the snapshot if HBase is online. Otherwise, you can also take a snapshot while the HBase is running, copy this snapshot or export this snapshot into a different HTFS, and then just run your MapReduce job from there. This basically is a I think, very good use case where basically if you're already like running your MapReduce job in a different cluster than HBase, then exporting the snapshot and then just running the scans over there is a good idea. Okay. So basically, the table snapshot input format gets a scan representing the query and restores the snapshot to a temporary directory. Restoring is just like copying some symbolic links, so it's a cheap operation. Okay, and then basically for each region in the snapshot, we determine that whether the scan has this sees this region or not, and then we create a split. Input split for this region, and then each record reader would just open the region in its memory, and then just does a regular scan over that region. Okay, but this feature, of course, means that we are bypassing the whole HBase layer and then going directly to the disk. So this means that all the HBase level access control definitions are also bypassed as well. So if you're using security and you're basically doing access control based on columns, column families, then this feature is definitely not compatible with it because you're bypassing everything and then giving the user who runs this job direct access to the files. Okay. So as a final note on this, we don't have to go to the details of this, but as you can see, on an 8-node cluster, we can achieve like on a MapReduce job, we can achieve like 300 megabytes per second, versus otherwise you would achieve this amount. I think this was the scan MR. So it's a 5x improvement on the scan speed. So if you have large-scale MapReduce jobs, you can consider this feature, which is a good improvement. Okay, and the last feature I want to talk about is the idempotent operations. Okay, so the idempotent operations is table get, put, check and put kind of operations are retryable, and retrying these operations are safe because at the very worst you can just double put. Which basically is okay in HBase because we keep multiple versions and everything. But if you're doing increments or appends to a single cell, the retrying would cause double increment. So here is how it goes. So your application basically does a put, and an HTable object does a put request to what's called a RPC client. So this is a connection to the actual region server, which hosts your region. Okay. And this call, this RPC call, basically normally on a normal operation, this call goes like this. It does an HDFS append, which makes the edit durable, and then it returns the result, right? But if you do a call and don't get the response back, you don't know what's happened, basically. You don't know whether the increment happened or not, okay? But the HBase layer still has to retry this operation because the region might be moved, the region server might have died, or something else in the network has caused a timeout. You could have got a socket timeout or something. So we basically do a retry. But doing this retry with an increment means that you could be double incrementing versus you would only want to increment only once. Okay. So for combating this, what we introduced is what's called a nonce. Okay? A nonce is a pseudo-unique identifier that's defined from the client side per operation. So this is, for example, table.increment would internally create a new nonce, which is kind of like a hash. And then basically this nonce is carried over with the RPC. Okay? So, and what we do is that the nonce is also cached in a window, which is a 5-minute window. Okay, so if the client retries this this same operation, this same RPC on a different server or on the same server, it will be rejected. So this means that basically you won't be doing double increments or double appends for the same query. Okay, so basically the nonce is created here with the increment, and the nonce is carried over here. The region server caches this nonce and also writes the nonce to the write-add log. And when the region is lost or something, we replay the write-add log, and then we recache the nonce in the other region server who now has taken over the region. So that even if you're retrying over different servers, the nonce is kept in the cache so that the double increment is rejected. Okay, I think that's the end of the talk. If we have time, we can take a couple of questions. Sure.
These nonces are only kept in memory, are not written to the H files?
They're not written to H files. They're only written to write-add logs. Okay, so still some edge cases means that there are some edge cases where you would do a flush but don't replay the write-add log. Since the nonces are not written to the H files, you can have a rare condition where you would lose the nonce, although because you did a flush and then you won't replay the log again. But this is adding that to the H file is also a lot of overhead. So it's kind of like a trade-off at this point. Uh-huh.
Question, with the namespaces, does that mean you can have the same table name in different namespaces?
Exactly, yes. Can you repeat that? Sorry. Mm-hmm. Mm-hmm. So basically, you cannot at this point because of the fact that you want that to be automatic. Because if you don't want to go into that detail of like controlling the ranges of different things. But what you can control is you can just like the region split policy, you can control the sizes when a stripe basically splits into two. So that by doing that, you can control the stripe boundaries.
So this can be used as continued to idea of fixing region split.
Come again?
So this can be used as continued to idea of fixed region split.
Yeah. So basically, like once the idea is to the stripes would continue splitting and splitting, and at some point in time, the region itself would split and be made into two. Okay. So thanks a lot. We can do an offline Q&A as well. Thank you.